Okay, welcome back. In this session, we are again going to talk some basic stuff only. We are going to talk about physics-informed machine learning with Modulus. Okay, Modulus is a platform on which you do physics-informed machine learning. Now, why this is important? Because these are the some of the models which are used in later weather models and things like that. Okay. So we'll generally discuss what is modulus, what is modulus architecture, and what is it involves in training the neural networks. Then we'll discuss about physics-informed neural networks in modulus. Then we'll discuss some things about data-informed neural networks and some other features, okay? So traditional NWP or traditional HPC, you always use simulations. Now simulations were developed to replace direct experimentation, okay? So you have certain experiments which are running that can be very costly. So replacing those experiments, you are replacing them by numerical simulations, which can be done. But even numerical simulations also become, after some time, become unfeasible because they have a lot of problem size can become arbitrarily long as you go to denser and denser grids. You know, the number of points explode, and then number of points explode, the number of computations which is required is also explodes. And you have various, if you don't go to those finer levels, then you are going to miss out on geometric details. Basically, if you have, say, uh, of this size, if you have a grid of this size, then you are going to miss out on those finer dots, right? To capture those finer dots, you need to go to that scale. And if you go to that scale, number of points will simply increase. So number of points, the geometric details can be captured at finer grid levels, and but the downside of it is the amount of computation increases tremendously if you go to the geometric details. Number of designs also is matters a lot because you are basically taking a wider scope or wider field of parameters. Those parameters themselves define the number of designs, okay? And complexity in physics, basically more and more phenomena you want to capture. So those can be multi-scale or somewhere how to parameterize those multi-scales and things like that. That increases the complexity of the physics, okay? So that's why these methods, normal simulational methods, are computationally expensive. And they are also plagued by the discretization techniques. As I said, that you have to go to finer scales if you have, and those discretization, somewhere basically you might be spending lot of computation on the places of regions of no interest. There will be smaller regions of interest where the details are there, the more geometric details are there, because you wanted to capture that. If you discretize the whole at the same scale, then a lot of computation is spent at places where there is um, no details or no things of interest being occurring there, right? And the simulation techniques are also not suitable for data assimilation and inverse kind of problems, where from the data you want to generate the physics. So those kind of problems, it is not suitable, okay? So NVIDIA provides a toolkit which does. Now, the people came up with the idea that neural networks can be good emulators, okay? So you have generally physical systems you characterize by having some equations or partial differential equations which characterize some physical systems. Now these physical systems, the equations need to be solved to evolve the system or do the simulation. Uh, People thought that since neural networks are actually good at emulating things, they thought that they can replace the solution of those equations by replacing it by a neural network. So it can emulate that physical system. So that's why they came up with this idea. And then NVIDIA Modulus provides a framework to do the same thing. You basically want to build a neural network which emulates the any physical system. Okay, so it provides all the facility to do that. Okay, it has AI toolkit which provides different kinds of neural networks. Basically, you can inbuilt. Then it has performance which is scalable because it is provided by NVIDIA, so it will be accelerated on GPUs in any case. So it basically in turn uses the libraries and all which efficiently utilize the underlying hardware. And since the GPUs, we saw that for massively parallel things, the GPUs are better. We just saw that, right, in the previous lecture. So that is why it is important to do it on GPUs, and it is inbuilt in this kind of platform, okay? It can be optimized for inference, and it can give you near real-time inferences. Once training is done of that neural network, you can do the inferencing very fast. And it has APIs so that you can adopt it for various, quickly adopt it for different kind of use cases. One of the first use cases was heat sink design, which was used in NVIDIA servers itself. So they used design optimized through this modulus, which optimized the airflow around the cooling of the GPU, the heat sink of the GPU and the cooling of that. And that was actually adopted in the servers. Okay, so traditional solvers like finite element, difference, finite volumes, all these things, solvers, modulus can also solve these things because it can make neural networks which emulate all these things. Okay, this we have discussed. Some of these results which seem to be very encouraging, okay. It closely follows the simulations. Then, yeah.
So compared to the open form is, I think, Fortran or C++.
Yeah, C++, correct.
What language you use in your modulus?
Modulus, the underlying libraries are in C, mostly in C, okay. C, C++, and the overlying is Python, yeah.
So inside the Python, you are calling these routines, C++ routines.
So it is built inside. Actually, you don't really call those things unless you it gives facility.
And the user can select.
No, not a GUI.
Yeah, you are going to show something.
Yeah.
How it looks like.
Yeah, modulus. So we'll take a look into that. Okay. But the advantage is that once this emulated network are developed, are trained, then you can do inferencing really fast and then you can use it to generate digital twins.
Running on GPU,
yeah, it is. Everything is running on GPUs.
yes.
No, but it has facility to run it on CPUs also. Only thing, it will be slow. That's all. Yes.
That's why I have to NVIDIA.
Yes. And it also has APIs to develop data-driven machine learning, and discretized machine learning also is there. Okay. I mean, you can take the discretized grids and all that also. And you can also have super resolution from the low fidelity results. Okay, so modulus is PDE solver, partial differential equation solver. Directly you can solve partial differential equation, and that is gridless. Okay, you don't require grid to do that. And it is design and parametric space you can explore basically. So you can do design space exploration also, because design is what? It's set of parameters, right? Inverse problems also you can solve. So there are different categories actually here. Completely numerical solver, yeah.
PD solver, is it anyway faster than I use any other package that implements the CUDA toolkit? For instance, if I use torch instead of modulus, is modulus in any way faster?
It is. It is emulator, no?
What is the basic difference between, say, a spectral method using torch in some PD? I don't understand what they mean by emulate.
See, PDs you can directly solve by discretizing on some geometry. You say discretize, you make a finite difference or finite element or whatever, and then solve it step by step. That way you can solve it. That is called simulation. Yeah. And there is what you are doing is, instead of taking that PD, you are making a neural network to ingest physics into it, and then that neural network itself will give you solution. You say that initial conditions are so, and my final output should be so. So, and you are training the network with that. So once you have trained that network, huh?
We have to train it with simulation data or only the.
Yeah, so you can do it with only equations also, with and boundary conditions also. Okay, that will take it up. You will soon see. Okay. So data assimilation problems and data driven solutions. So there are 2-3 categories in which this you have no data or very little data, just the boundary conditions and no data. In this, there is some amount of data, and this you have lot of data, and basically you want to have completely data driven solutions. Okay. Okay, for the time being, I'll skip. I will come back to these slides. Okay, later. Okay, I wanted to come to this. Okay. Let me just. Okay. So this is the equation which we are trying to solve, which is simple enough equation. Okay. And now if we had data, so we have data only solution. So we have 4-point data here, okay, on which we are trying to solve using this modulus or the pins, okay. And we have made a loss function, which is this loss of data. If you run this code, this is the actual solution, because this equation can be solved analytically also. So this is the actual equation solution, but the region where the data is there it follows it closely, but as soon as the data region is over, there it will not follow or might not follow. Okay. You have data and physics. You make the loss function in such a way that this L physics loss, this loss is on the points interior to this, any sample points, okay? You basically define an interval and then you just define this loss. And if you solve it, you find that this follows closely. And in this, there is no data. Only two boundaries are given. That U0, U1 is 0. These two boundaries are given. And you solve this equation just by this physics loss. Then you find that it follows quickly, closely that. Yeah. So torch will generally, so there are 2-3 things. If it is also making a neural network and this modulus is also making neural networks might be the same. And on CPUs, they will work the same way. Modulus is a specialty that it already integrates with GPUs. So for simple functions, you might not see the time difference and all that. But if you go to some complex geometries and slightly bigger domain, you will start seeing the performance difference because that torch thing will run only on CPU and this will run on GPUs as well. So GPUs, it will be much faster.
We can run torch on stick. Torch.2 device.
Huh?
We can run the torch program also in GPU, right?
Hmm.
Python program using torch 2 device code CUDA.
Yes.
How the difference is coming with torch and modulus? If they both run on.
If they both run on GPU, then they will give it. But everything you will have to code by hand. Torch to device and all these things you will have in modulus. It just provides a framework to give all those facilities. Huh? Yeah. Okay. So basically, this thing is we give it as a workshop with hands-on. So this portion is that you construct the solution. You actually construct in that Jupyter notebook. You actually do the construction of the solution of this thing, and that program is given. Okay. And you try to solve this. You can also do the parameterization also. Okay. So you form the loss functions and all that. Okay. So after sufficient training, you will find that this function is actually given by this true solution is this simple solution, which you plot and you plot the trained neural networks solution. It is follows it quickly, closely. Okay, but only thing is using the this neural networks, you can vary the boundary conditions and see the solutions. Okay, that. Okay. So you were asking for the code, no? This is the code which it specifies some load hydra with these hyperparameters. Some things are given, this YAML file. In this, it is given, okay? You say that decay rate is though, decay steps is so, save files and all that. You load the hydra and then this is the step basically you are performing. Then you define the geometry, load data sets, and then create domain, create nodes, and constraint and all that you need to create. So which are there in the next steps. Yes.
Like other.
Yeah, it's like SimPy. Most of the people will be familiar with SimPy here, right? So you define the geometry and things in SimPy. You define the equations also. You also define the network here. You say that fully connected arch, so you are choosing the network here. You are saying how many layers, layer size, all those things you are defining here.
Some hybrid grid, for example, is non-conventional gridding possible? For
Grid.
example, at some, for instance, I have also time derivatives in my equation.
Huh.
I would sometimes want very small, in time direction, very small grids. So that
This is not gridded. This is not gridded. So you are directly emulating. There is no finite difference or anything involved here. This is non-grid architecture to solve. Direct solution of partial differential equation, just the boundary condition, no grid involved. There is no grid, no discretization.
time derivatives are
Yeah. Time and space, both derivatives are included in this. There is no discretization. Huh?
there would be then some resolution constraint.
Resolution constraint is non-grid, there is no resolution constraint. But yeah, if you want to go to grid, it becomes actually more computationally intensive. So people do go to gridded for say Fourier domain and all that. Then it becomes slightly more computationally intensive. But for direct partial differential equations, you don't require grid. Unless you have data, no? If you don't have data, you don't require grid. If you have data, then you require grid because those data points will be on some grids. So here you are defining the constraints, okay? And you are saying that boundary constraints, point-wise boundary constraints, and basically you are saying that you outwear.
Sorry,
Huh?
boundary constraints will be our data.
Huh?
Boundary constraints will often be our data.
Boundary constraints is just that two boundaries what for this is single dimensional problem, no? So two boundaries. Huh. Some geometry is there. Some geometry is there. For example, these steps. Then those all will be data points, yeah.
That will be graded. We'll start with a graded.
But inside there is no discretization involved inside, no? So boundary places you are gridding it, but inside there is no grid.
I'm just concerned because here it's only 2 points are the boundary condition. It looks very nice. But if you have a whole field of boundary condition,
That will be gridded. That will have grid points, at least at those geometry you have to import. But between that interior fields, that is just the boundary conditions. At interior fields, there will not be grid. Because you are not doing finite difference or finite this thing here. You are just directly auto differentiating you are doing. Huh?
How do you define convergence?
Convergence of?
Solution. You found a solution this way. Let's put in a nonlinear PDE and you found the solution. How is it converged? How do we trust the solution we get? In a numerical solver, you refine the grid in space and time.
Yes.
And you get solution to converge.
Yeah.
Here, how is convergence defined?
So basically, you are training a neural network to emulate your physical system. Okay. So believability comes from you take up a known problem and then try to solve it, okay? You are not taking, currently at least you are not taking the unknown problem. Once you come to unknown problem, then how do you believe? That is your question, right?
Yes.
So how closely it follows the observations or how closely it follows the data. Then you have to check with the data. So you have in any neural networks, you have, he described, no, that you have training data, testing data, validation data. So validation data, you check how closely it follows that validation data. Then you know that it is converged solution.
So you're trained on these kind of PDs already. You're not trying it on new PDs. Is that right? The
Means
solutions you're generating.
you have, either you should have a data. You are not, you have to have data, right?
Yes.
So
Then the question comes, if we have the full data, we can go the data-driven approach. But here we are solving the differential equation with the initial and boundary value problems.
yes.
I think that is question
Right.
related to
Right.
that.
So that's the question I'm asking, right? So for example, CumSol, right?
Huh?
CumSol or ANSYS Fluent.
He is actually talking of pins, where actually he says pins the physics driven, the error convergence that we're talking in the, it's because of the pins, they come in the loss function definition, which I think it will be built into the program somewhere.
Yes.
So that's
Yes.
actually the convergence criteria, but I think he may come sometime later.
Okay.
So that actually the convergence is taken care based on the loss function.
So the
Loss
loss function
function.
has the PD inbuilt in it.
Yes, yes.
Yes.
Have the governing loss go into the loss function.
Yeah,
Loss
that we,
function will, I think, sir, better. Loss function will consider all your boundary condition, initial value from initial conditions, and then
Yeah, just bring it. He's coming.
Yeah,
Yeah.
Okay, then yeah, why don't you finish?
this is the loss function, no? Yeah.
That's what he's asking.
Yes. Okay. This is the loss function which is there.
So I initially we have to take some data, like initial and then we train the. I mean, I am not the expert. Maybe that is
The boundary conditions are there.
Boundary condition is
boundary
there,
data.
that's,
But initial some data is required. We don't have the grid, but we have the points. So
That's
that
fine.
data we have to have.
So that's not, as he rightly said, you don't need a grid. You can randomly choose the points inside the domain at which you are trying to find the residues. This color.
yes.
So that's how it is a gridless.
Gridless. So randomly what the solver does is that it will keep on choosing random points in the interior, okay? So boundaries are fixed, okay? Boundaries are fixed. Those 2 points are fixed, okay? Those are boundary because this is a hard bound, okay? Then you have inside, you have some random points. You take this 4, then this 4, then this 4, then this 4. At those values, the residual of this physics residue should become minimal. That's how you train. The training part involves that residual of that physics is minimal. Once that has become minimum, then you say that it's trained, and then you try to validate and check. So yeah, so now I think it is right time to go back to this, okay? So geometry and data is imported first, okay? Here, geometry, it can be very complicated geometry also. Fairly means it can be complicated. Actually, people take from the CAD design. CAD design means from Omniverse, people take in the design, point cloud designs, and put them as a boundary condition, because CAD designing means they can design this, say, podium or this table or this entire hall and take that as boundary conditions, okay, and import that. Then you can have ways to import the data. Also, it provides a facility to take in different kind of neural networks, okay, and you can define nodes, structure of nodes. It's a fully connected neural network or Fourier feature or FNO, deep you can take any kind of neural network, okay? Then you have physical laws and PDEs that also you can built in into the loss function. These physical laws and PDEs are built into the loss function here. Okay, boundary conditions, physical PDEs, data, all three are made into separate loss functions. They are all added, of course, later on. Okay. And this constraints then make a node graph, okay? Then you define a solver, training optimizer here. You can put monitor, validator. These are all fancy features which you can use to see how the model is converging and all that, okay? And then you can have an inferencer. So this is the things which we are trying to follow in the solution of the next, okay? So how do you deploy it? You take a neural network, you put in PDs as a constraint, as a loss function here, okay? Physics loss, data loss, you can put constraints. Whatever data you might have, that can be used to also give the loss function, right? Even that will be added. And with the help of those, actually you can do parametric studies. So if you have some amount of data and physics loss, but in physics functions you might have some uncertain parameters. For example, one term has a coefficient which is not fully known. In that case, that parameter also you can try to guess if you have some amount of data. So we saw that this load hydra part in which you are just putting in some hyperparameters here, which can be also be changed. These are some things which are loaded by default, but you can also change them. Then you define the geometries with the help of geometry and solution domain with the help of SimPy, and you can define the equations, and it will actually make the loss functions by itself, but you might have to just define the PDs. And the boundary constraints, you have to put interior constraints also. You can put interior constraint is nothing but the PDE. And then you just make a solver and give it to solution to start solving the, run the solution and train the network, okay? That is the part where we run actually the Jupyter notebook and do that. Okay, so here we are trying to, instead of solving that earlier we were trying to solve this is equal to 0. Here we are trying to solve it is equal to fx. And we are trying to construct, if we have some data point, we are trying to construct what is, fx is nothing but source function, right? In this differential equation, fx is source function, and we are trying to guess the source function from the data which we have. So if we have some data, then you can try to guess the source function. And if you put the loss function and train, actually it will give the, you can also guess about the source function, okay? So if you have, say, varying boundary, fx is equal to 1 for different values of L, okay? So boundary conditions itself we are varying here, and we are doing a parametric studies on that boundary conditions variation. And all the solutions it can be done. So these are some of the advantages of the spins actually. Once the neural network is trained, then you can do these parametric studies very quickly. Inverse function is trying to guess the fx, okay? This equation it is also trying to solve. using the neural network. You can build a neural network using modulus and then try to solve this equation. And actually you find that it quite closely follows the FNet, means neural network follows quite closely the source function, which is analytical solution is available. Similarly, you can do 1D diffusion, lot of things you can do. Actually, if you want to go through that training, we can hold this training session also for that, in which everybody will get access to Jupyter Notebook and they can do all these problems hands-on and try to solve them. Some of these slides I'm going to, because they are more training specific. This is just an example how it looks like that, how the code snippets look like. Let me go to further. So in modulus, there are facilities to do FNOs, Fourier neural operators, and AFNOs also. Okay. Basically, it has lifting and downwinding operator. Okay. And it requires grid also. Okay. And this is the code snippet in which you are doing the FNO. Okay. Lifting layer, Fourier layer, and then decoding network. You can get the solution back. All these facilities are there in modulus. So if you have this is required, then you can use this. Then the Fourier network depends upon the convolutional networks, but this is dependent upon the transformer architecture. Okay, AFNO. This is basically used in the forecast net. Then there are GNOs and PINOs also, which are available in modulus. Graph neural operators and the physical neural operators. Okay. I'll change the presentation to this thing.
No, okay, no. Okay.
Yes.
Are these completely on the system packages, or do we require NVIDIA server, or does it communicate in any way to?
So ForecastNet or Earth2 system, it communicates to that. It can run on cloud, or you can also install it on premise. But Modulus is a container which is available from NGC. You can download and work on it.
And if we have very, say, very high resolution simulations with time derivatives, that might not work on our clusters. Is there a method to?
Generally, if you have very high, which requires good amount of GPUs, then you have to have those kind of systems. Otherwise, it will run very slowly. That's all. Because it's all parallel, right? So it can be cut up and given. Okay. So if it takes 1 hour, it might take 10 hours or something like that.
And also, ForecastNet previous version, they were available on use on your own system. That kind of setting. Now without,
Yes. ForecastNet is available. So you can also have based out of your system. Yeah, that is possible.
Models can be downloaded, anybody can download it, it's a container and then.
It's open source, it is container, you can work on containers.
So then,
Yes, yes, yes.
or we can search on Google, we will get it. After PDF.
Huh?
We can search on the Google, we'll get it.
You'll
Or
get
you have
it
any
on
link, a
NGC.
special link to download.
NGC, just search for NGC, go to NGC and search for modulus. That entire,
Rename
but yeah,
No, what did you say? Can you repeat?
physics Nemo.
Physics?
Nemo,
Nemo.
yeah,
So that is the modulus physics?
yeah, that is modulus inside it.
NVIDIA physics Nemo. Okay, so this is like a prompt engineering. So I want to tell to the students, you just type the physics Nemo, you will get this modulus. You can
Yes.
download. It's a container, so you can take the container and install in your laptop or whatever
Yes.
system.
Yes,
This is
yes,
very good
it will
information.
work out for on CPUs also, so it,
Yeah.
nothing is there to means
Yeah.
so works only. It just works faster on GPUs. That's all.
Thank you. That's good information.
Any other questions? Okay, if not, let's thank. Okay, if not, let's thank Prathu for this very engaging lecture.
Thank you.
And this, I think today, like we had lots of talks in the, especially in the second half, first by Bipin and then by Prathu about the various practical and computational aspects of what the theoretical ideas which we have learned so far. So I think these are also very essential components of this whole package. So yeah, thanks a lot. Thanks a lot for Prathu who is representing the NVIDIA. And so with that, we have come to the end of today's session. And